Welcome to massive open online course on basic principles and calculations in chemical engineering. So we are discussing about basic laws of energy equations and basic equations, how to calculate that energy balance for a particular system. In this lecture under the module of some energy balance on non-reactive processes, we will discuss the problem based on that mechanical energy balance only. So we have discussed that basic equation for that energy balance, and from which we will be calculating that mechanical energy. Also we have discussed about that heat of formation and heat of reaction, heat of solution, all those things in our previous lectures. In this case we will try to derive that mechanical energy balance, and from which we will also try to understand that Bernoulli's equation with some examples. So what is that mechanical energy balance? This is basically useful for process in which changes in the potential and kinetic energies which are primarily interest rather than changes in enthalpy or internal energy or heat associated with the processes. That is why this mechanical energy balance will be mainly used for purely mechanical problems, that is problems in which heat transfer, chemical reactions or phase change are not present in that particular processes. We have already discussed that generally how that energy balance for the open system can be represented. Here in these slides we have given that for an open system there will be a heat energy to be supplied to the system, whereas by this system some work will be done, and in this system also there will be some mass flow rate, and also you will see that there will be a change of velocity, because of which there will be a change of kinetic energy, and also the position of that system in a particular level based on which there will be a certain change of energy that will be regarded as potential energy, and also due to this heat energy supplied to that open process, and based on which you will see that there will be a certain change of energy in the system that will be regarded as internal energy, and also you will see that there will be some flow energy will be working on this system because of that change of volume of the system, or because of the change of pressure in the inlet and outlet position. So based on which you will see there will be a certain change of energy, and that is called that flow energy. So upon all those terms, considering we can write that energy balance equation for the open process, like that what will be the change of internal energy, what will be the change of kinetic energy, what will be the change of potential energy, what will be the change of flow energy. That of course will be is equal to that what will be the net energy supplied to the system. That means what will be the heat energy supplied to the system, and also what will be the amount of work done by the system. If you subtract these two quantities, then you will get that net energy supplied to the system, and this net energy supplied to the system will be equals to summation of all changes of internal energy, kinetic energy, potential energy, even flow energies are there. So in that case whenever that system will be working, that the net of work done by that system actually will be summation of two works done, that will be so it is called the shaft work, and another is called flow work. So here we can write that the flow of work done by the system, that will be equal to summation of this shaft work and flow work. What is the shaft work? This is basically the rate of work done by the fluid on a moving part within the system, like piston, turbine and rotor, Whereas flow work, this is basically rate of work done by the fluid at the system outlet minus the rate of work done on the fluid at the system inlet. So this will be called as flow work. So this flow work is basically rate of work done by the fluid at the system, that will be at the outlet, and if you subtract that the rate of work done in the fluid at the system inlet, you will get that flow work, and this will be regarded as actually P out into V dot out minus P in into V dot in. What does it mean? That what is the pressure at that outlet condition, and what will be the volume at that outlet condition, and what is the pressure in inlet condition, and what will be the volume in the inlet condition. So if you are considering as a rate, P you cannot regard it as rate. So in that case only volumetric flow rate you can consider there in the outlet, and also volumetric flow rate in the inlet. So finally you can say that V dot into P minus V dot into P in inlet condition. If you have this, then you will say that total flow work will be defined by this quantity. Now if you have that several input and output streams, then flow work can be regarded as the what will be the summation of that flow work at this outlet condition, and what should be the flow work at the outlet condition and input condition there. So subtracting the summation of that input flow work and output flow work, we can get that what will be the total flow work for this several input and output streams. Now from these terms we can make the general energy balance equation for an open continuous system in terms of rate just by here. In this case we know that accumulation will be equal to input minus output, and if it is continuous, then we can say that accumulation will be equal to input rate minus output rate, and the rate of final system energy minus rate of initial system energy, that will be equal to rate of net energy transferred to the system, that is in minus out. So based on which we can write that rate of initial system energy, that will be that summation of internal energy, kinetic energy, potential energy, and flow energy or flow work at that inlet condition. Similarly, for the final system energy, we can have that summation of internal energy, kinetic energy, potential energy, and that flow energy or flow work at that outlet condition. So energy transferred, actually basically it will be what will be the heat energy transferred and what will be the work done by the system, and if you subtract this, you will get that net energy transferred to the system. Now this net energy transferred to the system will be equal to here that net energy, that is in just by rate of final system energy minus rate of initial system energy can be equated, and finally you can get that here difference in that internal energy rate, difference in kinetic energy rate, difference in potential energy rate, and difference in flow work rate there. So summation of all these differences of this internal energy, kinetic energy, potential energy, and flow work, then it will be is equal to that net energy transfer to the system, that is inlet and outlet condition there. So in this way we can have this general form of general energy balance equation for an open continuous system, and from this you can write this here more concisely like that that rate of internal energy change will be equal to delta U dot, rate of kinetic energy change will be equal to delta kinetic energy dot, here delta Ke, here similarly potential energy rate change, it will be delta Pe, and flow work change rate will be equal to that delta into PV dot, that will be equal to Q dot minus W dot. Here in this case this is given each terms, what will be the definition of that each terms here given in this slides. So remember this here, this internal energy change plus this flow energy change will be equals to that or will be denoted by, or will be defined or will be referred as, or will be known as enthalpy change there. So this enthalpy is basically the summation of internal energy plus flow energy there. So rate of change of that enthalpy will be equal to rate of summation of rate of internal energy plus rate of flow energy change there. So this equation will give you that general energy balance equation for the open condition at continuous mode. And from this general energy balance equation at a steady state, we can write this equation here. From this you can write this internal energy, kinetic energy, potential energy, even flow energy in terms of its specific energy rate there. So in that case, a specific energy can be represented by this term that you had. Similarly here in the inlet condition it will be U hat in. So we can write here this at inlet and outlet condition, what will be the change of that energy there. We can write this equation in terms of specific terms by taking the mass flow rate as a common factor here. So from this we can write this equation, and we can then express this equation that will be equals to Q dot minus W dot S here. Here in this case, flow energy has two components. One component is going to this side, so that is why we can write this in terms of that specific terms there. In this case here V, small v whatever represented here, in this case this will be specific volume, that is 1 by rho. Whereas here this V we can write here U also, this here velocity as U, so this is U. And so what will be the velocity change in the inlet and outlet condition, that will be regarded as what is that kinetic energy change. And since kinetic energy is defined by that half m u square, so here m is common factor m dot, so it will be kinetic energy change. So half into m dot into u square. At the outlet similarly half into m dot into u in square, that will be in your inlet condition, that what will be the kinetic energy there. And since here rho is the density of the material, if it is constant for incompressible fluid, we can simply then consider that here it will be that V that it will be that constant there. So only that because of pressure change that you can get that flow work there. So in this way we can write this general form equation in terms of specific terms by taking the mass flow rate as a common factor. Now after considering that incompressible flow rate, so that the density is constant, so we can write here V in that will be equal to V out, that will be 1 by rho. Similarly also let us define here that delta U hat, that will be equal to here U out hat minus U hat in, that means specific internal energy difference of this outlet condition from its inlet condition, and delta P will be regarded as P out minus P in there. With these changes, the general energy balance equation can be written as here like this after simplification like this. In this case here minus W or dot S by m dot, this is basically shaft work preferred by the system on the surroundings per unit mass of material that is passing through the system. Similarly, this is your pressure work, and this is your kinetic energy and this is your potential work, and this is what is that internal energy, and this is your that heat energy per unit mass. So the term in this case, in the absence of chemical reactions, the phase change or other sources large amount of heat transfer wise, generally we can represent heat generated due to the viscous friction in the fluid. In such situations, this term is regarded as that loss and denoted as F. So what we can write here, these total terms, that delta U hat minus Q dot by M dot, that will be regarded as that F. This F is called friction loss. So finally you can have this equation of energy balance equation in terms of that frictions. This total energy will be equal to here what will be the the shaft work preferred by the system on the surroundings. Now let us do an example with this mechanical energy balance equation. So this is basically mechanical energy balance equation. So in this case, if we consider that water is supplying from a storage tank of a filtering plant of a common tank of house complex in its roof by a pump at a rate of 0.2 meter cube per second after its filtering, and the elevation of the surface of the storage tank is 410 meter. The elevation of the tank of house complex is 450 meter from sea level. The water discharge pipe is located at a depth of 10 meter from the source of the storage tank of filtration plant. The frictional losses in the water line to the plant are given by a relation 0.01 meter per second square into L, where L is the length of the pipeline. The water line to the supply tank has an inner diameter of 0.1 meter and length of 1000 meter. Now how much energy must a pump deliver to the water destination tank there in the house complex? In this case, basically what happened, that water to be supplied by a pump from the water storage tank, which is kept in filtration plant, from which that filtered water to be supplied to a house complex by this pump. Now in this case, that discharge line of this pump is certain distance from that water level of that storage tank. It is given, it is 10 meter that above this discharge line, and also this tank, this storage tank is it is in a level of 410 meter high from the sea level, whereas the destination tank of water in the house complex it is 450 meter above that sea level. And also it is seen that the based on this level difference, you can say that the discharge line from that pipe is situated 50 meter below that destination tank, or you can say that the storage tank water level is 40 meter below that destination tank of that water in the house complex. Now at this condition, there are certain frictional losses will be there whenever water will be flowing through the pipe. The rate of frictions is given here. If your acceleration is 0.01 meter per second square, then you have to multiply by the length of this pipe, whatever required total length, to get the frictional loss as 0.01 meter per second square into length of the pipe there. Now in this case, pipe diameter is given 0.1 meter inner diameter, whereas length is given 1000 meter total length. So at this condition, what will be the energy must a pump deliver to the water so that it will reach to that destination water tank there in the house complex. Now in this case, how to solve this problem? we know that mechanical energy balance by this equation here we have already described. So, based on this mechanical energy balance, you have to calculate what should be the energy required to supply that water from that storage tank to the destination tank there. So, this minus W dot S by m dot, that will be equal to delta P by rho plus delta U square by 2 plus G delta Z plus F. In this case, first of all you have to find out what should be the mass flow rate. So, what is the mass flow rate here? Let us calculate here. So, m dot, we can write m dot will be equal to mass flow rate. So, this is basically, it is given as 0.2 into 1000s. So, that will be equal to 200 kg per second. So, this is your mass flow rate, and the elevation change, is 50 meter. Elevation change is 50 meter as per diagram given, here. So, so we know that this mass flow rate. Next we have to calculate what should be the pressure change. So, what should be the absolute pressure change? Absolute pressure change we can calculate as delta P here. So, that will be equal to simply P2 minus P1. As per diagram, this is your P2 at that level of water at the destination tank, and this P1 from where this water is sucking by this pump or delivering that pump. So, this will be equal to delta P will be equal to here P2 minus P1. So, it will be equal to what? What is P2 here? Since it is atmospheric pressure, P2 101,325 minus what will be the P1 here? P1 is here 1000s into 9.81 into 10. This is 10 meter height. This is your that pressure there of this water pressure. What is the water pressure at this point? P1 by this level of this water in the storage tank, plus this is plus atmospheric pressure 101,325. This is your atmospheric pressure, this is Pascal. So, finally, it is coming as what is that? Minus 98100 Pascal. This is your absolute pressure change there. So, we can write this as per equation here. We can write minus then Ws dot, that will be equal to here we can write here delta P minus delta P by rho. What is that delta P here? This is 90 minus 98,100 Pascal divided by rho is the density of water here, plus kinetic energy change. What will be the velocity there? It is given this velocity, we can have this velocity from this flow rate. We can calculate here this velocity here 15.92, that will be square minus here initial velocity 0 divided by what is that 2. So, this is your velocity difference. So, based on which you can calculate what the kinetic energy it will come, and then plus potential energy. What is the potential energy terms here? G is 9.81 into what is that delta Z, what is the elevation change, there it is I think 50 meter it is given, plus here frictional loss. As you know that as per problem that frictional loss is depends on that acceleration of the water and the length of the pipe. The acceleration is given 0.01 meter per second square into length of this pipe is given 1000. So finally we can get this that delta P by rho and what is the kinetic energy change and also potential energies and frictional energy. So after that you have to multiply it by mass flow rate, that is here, what is that mass flow rate here, m dot, here it is given as what is that 1000 here 200 kg per second. So we can then finally have this as what is that 105 here 124 watt, that means here joule per second, we can write here watt there. So in this way we can calculate what should be the energy supplied by that pump to deliver this water to the destination tank. Let us do another example here, like suppose a pond water is supposed to use for fire extinguishment in an institute for an emergency, if any such case. In that case the water is to be used by a pump and then delivered to hoses. It may be desired to deliver 2000 liter of water per minute at a pressure of 15 bar gauge. If there is a 5 meter elevation change between the water level in the pond and the discharge of the pump, in that case no change in the diameter of the pipes and hoses, and if the pump has an efficiency of 70% there, in this case how much work must be supplied to the pump in order to meet that pressure and specified discharge rate to utilize it for the fire extinguishment. So assume that there is a negligible friction, so based on which we can then calculate again by this that general energy balance equation, where you can write here minus W S dot by m dot, that will be equal to what is that pressure energy change there. Here pressure is 15 bar, so you have to make it absolute since it is given as gauge pressure. So here 15 plus 1 bar minus 1, that will be your atmospheric condition. So this is your pressure change in terms of bar. So what would be the pressure change in terms of that here in Newton per meter square, then you have to multiply it by that 101325, then finally you will get this one. After that you have to calculate that kinetic energy, since here this velocity at the inlet and outlet conditions are negligible, or kinetic energy is negligible. In that case we can say that this difference will be 0, or you can see the same velocity of that inlet and outlet of this pump there of the system, then you can say that there will be kinetic energy change will be 0, whereas potential energy it will come because of that elevation. So you can calculate simply that G into here delta Z, and then friction is 0 here, it is neglected. So finally we can have this calculation of this this W S dot that will be equal to here, after substitution of all those values, then we can get this here like this 52.3 kilowatt. Now the pump has an efficiency of 70%. Accordingly the actual work that must be supplied to the pump in order to meet the pressure and discharge rate specification, then you have to divide this 52.3 by its efficiency factor, that is 0.70, then finally you can get that actual work to be done here 74.71 kilowatt. So, in this way you can calculate. Now, let us do another example, like water flows from an elevated container through a pipe to a turbine at a level, at a lower level, and out of the turbine through a similar pipe here as given in the picture in the slide. And you will see that at a point 100 meter above from this turbine, the pressure is 207 kilopascal, and at a point 3 meter below the turbine, the pressure is 124 kilopascal. Now, in this case you have to calculate the water flow rate, that must be if the turbine output is 1 megawatt there. Now, in this case how to calculate these things? So, again here you can apply that mechanical energy balance equation to calculate this water flow rate here. So, in this case what you have to do first, as per the problem, you have to see whether that is there any kinetic energy is there or not. Here velocity that will be same, since we are using that the same cross sectional area of the pipe. So, delta u square here, that will be equal to 0, and friction loss we can neglect here, a specific friction energy we can neglect here. So, f dot hat, that will be equals to 0. Then we can write from that energy balance equation delta P by rho plus G into delta Z, that will be equal to minus W S by that m dot here, like this, and from which we can write here m dot, that will be equal to minus W S dot by here delta P by rho plus G delta Z. So, based on this equation we can calculate what should be the water flow rate, that is B, if the turbine output is certain amount there. So, in this case what will be the W S dot here, this is given 1.00 megawatt. So, this is basically we can write 1 into 10 to the power 5 Newton meter per second, that will be equal to what is that, this is there, and similarly we can write here I think it is 1 megawatt. So, it will be, I think this is here 10 to the power 6 1 into 10 to the power 6 Newton meter per second, and delta P will be equal to here 124 minus 207 kilopascal. So, it will be equal to minus 83 kilopascal, and here that is basically minus 83 into 10 to the power 3 here Newton per meter square. You can write delta P by rho, rho is here 1000, that is density. So, it will be coming finally here minus 83, then Newton meter per kg, and then what is that delta Z accordingly it will be coming as what is that minus 103 meter, and G is given here 9.81 meter per second square. So, we can calculate Z into delta Z as here finally it will come here, what is that, 9.81 into minus 103, this will be is equal to 1010 Newton per Newton meter per kg, Newton meter per kg, and then after substitution of those values in the equation, m dot, that will be equal to minus W s dot by delta p by rho plus G delta Z, it will be coming as minus 1 into 10 to the power 6 divided by, this is minus 83 here, minus 1010, so it will be coming as finally 915, that is kg per second. So, in this way we can calculate what should be the mass flow rate of water that is flowing through the pipe and through the turbine, based on which there will be a energy supplied by the turbine there. Now, let us consider another principle of this mechanical energy. This is called Bernoulli's principles. In that case, in many cases you will see that the amount of energy lost to viscous dissipation in the fluid is small, that will be compared to magnitudes of the other terms in the general energy balance equation. In such cases you will see there will be a loss of friction. So, we can simply F can be regarded as 0. So, we can simply neglect that frictional energy. So, also in many common flows such as fluid flow through a pipe that do not have any appreciable shaft work that is associated with them, accordingly we can write that W will be equals to 0. So, for such frictionless flow where frictional contribution will be negligible, that we have considered that where that amount of energy lost to viscous dissipation in the fluid will be small compared to the other terms in the energy supplied or consideration. So, in that case we can say that if flow is that frictionless flow without shaft work, then we can simplify that mechanical energy balance into this equation here. So, we can simply that neglect that Ws, that will be equals to 0, and also friction will be equals to F will be equals to 0. So, here Ws that will be equals to 0 and frictional force that will be equals to 0. So, after neglecting these two terms, we can then write this equation here. So, this equation is called Bernoulli's equation, and the equation has a wide range of application despite its simplified assumptions. So, remember this, whenever this Bernoulli's equation to be applied to any system, that initially you have to that assess whether that system is ideal or not, that means frictionless or not, is there any shaft work is working on that or not, that also to be considered. So, simplified form of that mechanical energy will give you this Bernoulli's equation. What is this? You know that summation of this pressure, energy, kinetic energy and that potential energy, that will be equals to 0. What does it mean? That change of these three energies, summation of these three energy will be, you know, constant there. So based on these principles, we can, you know, solve some problems of you know some process like this. Let us do an example here. Suppose an aeroplane is moving at a velocity 250 meter per second at an elevation of approximately 8,000 meter. Now the density of the air at that elevation is considered as 0.4 kg per meter cube. The air velocity at underside wing here of that aeroplane has the same velocity of the aeroplane velocity, whereas the air velocity at the underside wing is 300 meter per second. In this case, calculate the pressure difference between the underside of the wing and the top side of the wing, that is necessary to lift that weight of that aeroplane to a height. So here basically we are having that the aeroplane is moving at a velocity of 200 meter per second at an elevation of 8,000 meter. The density of course will be changing along to that height. It is given that at that height it is 0.40 kg per meter cube, whereas the air velocity what is there in the underside of the wing, this is basically that same as that wing velocity there. It is basically 300 meter per second there. Now based on the you know velocity change at that elevated height, you have to calculate that what will be the pressure difference there. In this case we are considering that there will be frictionless movement of that aeroplane, and also there will be no shaft work done on the done by that system, and also there will be no heat energy supplied to the system there. So based on this we can apply that mechanical energy balance equation here. What is that equation? As per Bernoulli's equation, this is delta P by rho plus delta U square by 2 plus G into delta Z, that will be equals to 0. So according to this equation we can write delta P, that will be equal to minus delta U square by 2 plus G into delta Z whole bracket minus we can make it common here into rho, or you can write it here as minus U2 square minus U1 square by 2, that is velocity difference there, and then accordingly kinetic energy difference will be there, plus G into here elevation height here Z2 minus Z1 we can write into density. After that then we can write, after substitution of respective values of here velocity, here U2 is given 250 square, U1 is here 300 and then divided by 2 plus here plus G is 9.81 into Z2. Z2 is what is that? Z2 minus Z1 it is given, Z2 minus Z1, it is basically here the elevated height is 8,000 meter. So into whole bracket into density of the fluid here 0.40 after simplification or calculation we can have this as minus 25892. So, this is your that pressure difference as Pascal. So, this mass pressure difference will be there according to your problem. So, in this case we are applying that Bernoulli's equation and how to solve this equation based on this Bernoulli's equation like this. Let us do another example of this Bernoulli's equation. Like here one that nozzle is shown in the slide here, and water is flowing through a nozzle. Before coming to that or before flowing through that nozzle here, this is one nozzle at this point 2, and before flowing through that nozzle, the fluid is coming from a pipe at point 1. Now, the pipe diameter at point 1 it is given a certain value, whereas at this nozzle the nozzle diameter will be something different from this pipe. Generally nozzle diameter will be very smaller than compared to this pipe diameter. Now, pressure at point is atmospheric here at this point 2. Inner diameter of the pipe, or you can say that nozzle here at 2 is 0.001 meter there, and at this point inner diameter of the pipe is given at 0.01 meter. This is 10 times higher than that nozzle diameter. Pressure at this point is unknown to you, you have to find out, whereas pressure at this point 2 is atmospheric. So, there will be a pressure at this 2 point, and there is the elevation of this 2 point is 50 centimeter. There is no friction, it is considered. Water is flowing through this pipe and then nozzles at a rate of 20 liter per minute. Now, at that situation you have to find out what should be the pressure at this point 1 at its pipe here. So, let us again apply that Bernoulli's equation. So, before applying that we have to first calculate what would be the water flow rate in terms of volumetric flow rate in SI system first, meter cube per second, then only we can calculate. So, water flow rate, what is the water flow rate here? Water flow rate is given here 20 liter per minute. This will be is equal to 20 into liter, you have to convert it to meter cube, into 10 to the power minus 3, that means 1000 liter, that will be equal to 1 meter cube, divided by here 60 to be converted to second, then it will come as here 20 into 10 to the power minus 3 by 60, here it will be meter cube per second, and velocity at point 2, this will be equal to, this is your flow rate. If you consider flow rate is Q in meter cube per second, the velocity you can calculate just by dividing it by its cross sectional area at this point 2. So, it will be coming as, what is that velocity, flow rate is 20 into 10 to the power minus 3 divided by 60, then you have to divide it by that cross sectional area, what is that, pi by 4 into diameter at this point is 0.001 into that is square. So, this is your cross section, then it will come finally as U2 is equal to 424.41 meter per second. Similarly, you can calculate the velocity at point 1. The velocity at point 1 similarly for the same flow rate it is going. So, you can have 20 into 10 to the power minus 3 by 60 divided by its cross sectional area, it is pi by 4 into 0.01 here the cross diameter. So, it will be as here 4.24 meter per second. And what is the elevation here? Elevation is delta z, that will be is equal to z2 minus z1. This is here 50 centimeter, converting to meter it will be 0.5 meter. Then applying Bernoulli's equation, we can write applying Bernoulli's equation, we can write delta P, that will be equal to minus here u2 minus u2 square minus u1 square by 2 plus g into z2 minus z1 into rho. So, based on this we can calculate after substitution all the values of u1, u2, z1, z2 and g, all these things, and then density. Finally, we can have this value of pressure difference as 9 minus 9 0 0 5 9 1 7 3. This is in terms of unit as Newton per meter square. So, this is basically pressure difference. Now, as you know that this pressure difference is basically P2 minus P1, that is basically is minus 9 0 0 5 9 1 7 3 Newton per meter square, or you can say that it is Pascal, which implies that P1 will be equal to P2 plus 9 0 0 5 9 1 7 3 Pascal, okay, which implies P1 that will be equal to, what is the P2 value? This is atmospheric pressure. As per atmospheric pressure, we can say that it will be here 101 325 then plus 900 59173, that will be coming as 90160493 okay. Is it 93 or okay, it is, I think it will be here 8, and this will be considering as absolute. Why absolute? Because we are adding here with this value as atmospheric pressure here. So, finally, it will be coming as absolute pressure as P1. So, this will be equal to your pressure at that point 1 there. So, finally, we can write it as bar as 901 sorry 0.61 bar, because 1 bar that will be equal to 10 to the power 5 Newton per meter square. So, in this way, by applying the Bernoulli's equation, we can solve for pressure, we can solve for velocity, we can solve for even elevation height also, provided other terms are there as per your problem. Let us do another examples here. See, one figure is given in the slides. This case, water is flowing from a tank through a that converging diverging pipe. It is called Bernoulli pipe, and you will see that whenever this Bernoulli pipe is attached to that tank at this location, the diameter of this part of this Bernoulli is here at this d1, whereas at this converging section of this Bernoulli at point 2, its diameter is d2, whereas again from this converging section it will be converted to diverging as per that principle of Bernoulli for getting that lower pressure at this point 3. You will see that the diameter is d3. Here at these 3 sections you will see the diameters are d1, d2 and d3, whereas at this point 2 you will see that d2 is very smaller compared to that d1 and d3. This d1 and d3 will be the same diameter, whereas d2 will be the difference from this 2 and 1 and 2 point. Now, whenever fluid will be flowing through this Bernoulli meter, you will see there will be a change of pressure between point 1 and 2. Again you can get the pressure between 1 and 3 also. Again the pressure difference between 2 and 3 will be there. Because of that velocity change, whenever fluid will be flowing through that lower cross sectional area, their velocity will be higher relative to that higher cross sectional area. So, based on this velocity change, you will see there will be a change of pressure for a constant elevation height. Even if you change that elevation, there you have to consider that how much energy will be changing. So, based on this, what should be the pressure change or velocity change that you can calculate based on that Bernoulli's equation. So, pressure difference between this point 1 and 3 is given here 0.7 bar. By this manometer you can measure it. Cross sectional area at point 2 is half of that in point 3 here. Pressure at point 1 is 1.7 bar absolute. So, according to this problem, you have to find out what should be the pressure at point 2. Here pressure at point 2 you have to find out. Pressure at point 1 is given to here u, that is here 1.7 bar. Pressure at point 3 P3 is given, that is that pressure difference at P1 minus P3, that is given here 0.7 bar. So, accordingly you have to find out what will be the P2. Velocity also you have to calculate there based on this cross sectional area. So, let us apply that Bernoulli's equation. What is that Bernoulli's equation? You know that in this case what will be the z elevation here, since z1 that will be equal to z2. So, we can write here delta z will be equals to 0, u1 will not be equals to that u2 of course, since the cross sectional area is different, but u1 will be equals to 0 because the liquid is coming from that still condition from this tank. And then we can calculate u3 as what is that from that Bernoulli's equation as 2 into what is that P1 minus P3 by rho P3 by rho between this point 1 and 3. Then it will be equal to what, half. So, if we apply this Bernoulli's equation between point 1 and point 3, we can have this here j delta z will be equals to 0, and you know that u3 that can be calculated from this pressure difference, and u1 is it is 0. So, u3 can be calculated if you are having that cross sectional area at this point 1 and 3 are not same. Okay. And then what is that, even if there is a cross sectional area same, you will see that if the velocity at this cross sectional area is 0, then you have to of course calculate what should be the velocity at this point 3 there, because of that pipe cross sectional area. So, after substitution of this value, that means here 2 into what is the pressure difference between 1 and 3, that is 0.7 bar, you have to multiply by 10 to the power 5, then you will get the pressure in terms of Newton per meter square divided by density. Density is here water, then it will be density of water is 1000 after substitution, and then calculation we can get this value as 11 point 83 here meter per second. After that, if you do the mass balance between this point 2 and 3, points 2 and 3, we can have this A2 into U2, that will be equal to A3 into U3. What is that? A2 is the cross sectional area, U2 is the velocity at that point 2. That means A2 into U2 it will give you that volumetric flow rate at that 2, and A3 into U3 will give you the volumetric flow rate at that point 3. Since these volumetric flow rates are constant, so you can write this equation here, and from this we can write U2 will be equal to A3 by A2 into U3, that will be equal to what? Here A2 by A3 is given to you, A2 by A3 is given that 0.5 according to this problem here, because cross sectional area at point 2 is half of that in point 3. So, we can write A2 by A3 will be equals to 0.5. So, finally, we can write here after substitution of A2 by A3 and U3 value here as U3 is 11.83 divided by then A2 by A3 is simply 0.5, then we can have this value as 23.66, this is meter per second. Now, applying that Bernoulli's equation, again between points 1 and 2, we can get P2 minus P1 as rho U2 square by 2, which implies P2 will be equal to P1 plus rho U2 square by 2, that implies P2 will be equal to here after substitution of those values minus 1.1 into 10 to the power 5 Newton per meter square. So, that will be your absolute value. This is simply you can write 1.1 bar absolute. So, in this way we can apply this Bernoulli's equation for the different problems where we know this either of the values of this kinetic energy terms and potential energy terms or pressure difference terms there. So, we are having this Bernoulli's equation and solving those problems based on that general mechanical energy balance equation. I would suggest to read more about this general energy balance equation and solving the problems as suggested this textbook here in the slides for this course. So, I think you understood here in this lecture how to solve the problem based on this mechanical energy balance equation, and based on which you can solve more problems from this textbook. In the next lecture we will try to discuss more about this energy balance equation, where enthalpy balance will be considered without reaction and solving some problems. Thank you.